Welcome to Heriot-Watt University. My name is Tyger Donovan. I am the Head of Engineering and Physical Sciences on the Dubai campus of Heriot-Watt. And today I'm going to take you through a tour of our facilities and give you some insight into what it might be like to be an engineer here and the role that engineers have to play in society. So come with me as we take a bit of a tour around. And I'll start, I suppose, by welcoming you to engineering. We offer a wide range of engineering courses here in mechanical, chemical, electrical, energy, automotive, and we're bringing in new courses in robotics, autonomous and interactive systems, and we do this at both undergraduate and postgraduate level with MSc programs in renewable energy engineering and energy and advanced mechanical engineering. Just take a tour through our labs here on the left-hand side. So, come with me. Walking into our labs, most important thing, and I might just direct you towards our lab safety, very important to us, not just to keep everybody safe, which is obviously our utmost importance, but also for engineers, it is important that we design to be safe and we act accordingly. From the very first day you walk into Heriot-Watt University, lab safety is very important. So you'll see everybody wearing their lab coats here. We're not actually fully functioning today, but still important that we keep that health and safety culture going. So I'm going to walk into the lab here. And my role today is literally just to give you an overview and a tour of all the activities that happen in this workshop. So it's one of our larger workshops, and just to give you kind of quadrant by quadrant, we'll walk around here. On your left, you'll see some of our robotics. On the far distance there, some of our manufacture. We'll go around the corner then to look a little bit at Formula Student and our automotives, and you'll see these cars here, coffee lab, hydraulics lab, fluid mechanics, chemistry and chemical engineering. We'll do a tour of this lab. Now, one of the core tenets that we have in engineering is learning by doing, or experiential learning. Now, this obviously can't replace the lectures and tutorials that are very fundamental to becoming a good engineer. But the real learning, the real understanding often happens down here in the workshop. So we're going to see some of the activities that prospective students or undergraduate and even postgraduates do on a day-to-day basis. And we're going to start here with what is about to be launched, our new engineering degree in robotics, autonomous and interactive systems. So as we come around here, we're going to one of my colleagues here, Mohammed Al-Musta, and to our latest colleague, I guess, is Popeye.
Yeah.
So what exactly is Popeye doing here?
This is a short demo, and so highlighting the accuracy and the repeatability of robotics operation. Industry is now rapidly introducing robotics, and you can see Popeye is doing so many different functions in reality.
Okay, so I see here that you seem to be risking a lot of glassware here with Popeye. He's doing a lot of figure of eights, going around all this relatively expensive chemical engineering or chemistry glassware here. So you're ultimately confident that he's not going to knock these over or break them?
Pretty confident, yeah. Now robotics actually being used in even medical aspects, doing surgeries in remote areas. So they are that accurate.
So this is a good example of the precision and accuracy that even these kind of large-scale, heavy-duty robots can have.
That's true, because manufacturing facilities normally deal with thousands or millions of products. Take, for example, a car.
Yeah.
All that welded bodies, spray paints, and so on is being done with robotics. So you want that to be repeated over and over. But you know what? With all these robots, there will be always a human programming and doing that, and that should be you.
So when we talk about robotics, autonomous and interactive systems there, the autonomous part and the interactive systems, is there an element of artificial intelligence then involved in this whole, in these degree programs, and how important is that to electrical and electronic engineering?
Yeah, I would probably say that comes in levels. You start by manually controlling a robotic arm, for example, here. Then next stage is repeating everything after. But when you add the element where the machine starts to learn for itself using algorithms and AI, for example, artificial intelligence, it will accumulate all that experience to learn and do things better and better.
Very good. Okay, thank you very much for that, Mohammed. We're going to take a walk over here now and look at some of our automotives. You'll probably have seen behind me here that we have cars strewn about the place. Now you might be familiar with Formula 1, you might be familiar with Formula 2, Formula E, all these different formula that are out there, and they're all essentially racing competitions. There is something called Formula Student, and here's an example of one of our Heriot-Watt entries. So we have a team, it's called Heriot-Watt Racing, HW Racing if you want to take a look there. And this car has wholly been designed and built by our students across campuses. So this is an international effort of Heriot-Watt Racing. They develop this car here and they take it to track every year. They compete in Silverstone every year the week after the Silverstone Grand Prix. And it's seen as essentially the place where you do your internship before you maybe move into Formula 1 in reality. Now we encourage so many students to get involved in this irrespective of their discipline, because to develop a car like this we don't just need engineering and technical expertise, we need marketing, we need business cases, and all of this is so important to developing, you know, a successful car and getting it to track. Now this is a particularly exciting one for us. So if we just pan across to this side here on your right hand side, you'll see a typical IC or internal combustion engine. This is a typical petrol engine. Maybe it's not that typical, we've cut it apart and we're looking at how these pistons go up and down, and this is called the drivetrain, or sorry, the powertrain, the power unit for a typical car. This Formula Student car is the first one that we have developed in Heriot-Watt to have an electrical drivetrain if you want to come around this side. So this is an EV or an electric vehicle, and our students are developing it to compete this and next year. And what you'll see here essentially is our big power unit here. You have your suspension on the outside, typical units, and your battery packs, those are the red units in behind. This brings together so many different facets of engineering, from the structural. This airframe is a proper structure, to the dynamics, looking at the suspension and the to just even the aerodynamics. And we're going to in a minute take a look at how we develop an aerodynamic package for this, so we can reduce air resistance and you can make it essentially go faster. So if we go across now to one of our wind tunnels. So I'll introduce you to Mehdi. Mehdi is an associate professor in Heriot-Watt Dubai, and you're going to take us through here, Mehdi, I think, some of the scale testing. Would you say smaller scale testing?
You just mentioned about, you showed people the full scale car, and here we are testing the small scale of the cars that you see. So what we have here is a wind tunnel. There's a test section that you're looking at the moment.
Yep.
These cars actually are made by students, so through 3D printing, which I believe you're going to be...
We'll have a look at that later,
So students come up with a design, they build a 3D, so that's the first phase of design. And since the cost is very important in engineering, so what we do is we use the facilities like the wind tunnel to basically test the hypothesis that we have.
So instead of going to full-scale manufacturing design,
go into smaller scale to test
something small.
Idea.
So a student might have an idea or a design concept. They perhaps can somehow predict how it might perform, but they're not certain how it's going to perform.
Exactly. So they actually use wind tunnels to be able to test it. We can measure a couple of parameters like the forces, resistant forces like the drag force, which is linked with the fuel consumption, for example.
So explain to me drag force then, that's like the air resistance.
Air resistance.
Right.
So we're talking about the outside air. So when an object it moves in the air, how much resistance from the air.
Right. And generally you want to minimize that.
That has to be minimized because it's going to be directly linking with the fuel consumption.
And you also want to get the most power out of that engine.
Yes.
Right.
So it's all about the end efficiency, which is going to be maximized.
So this car here has been designed by one of our students. Yeah. They mounted it in the wind tunnel. What happens next?
Now it's connected to this device, which is just a basic load cell. It measures the two components of the forces, lift and drag. Once you turn this wind tunnel on, the air is going to be dragged in by the...
Okay, so if we look here, so this funnel here, the air is dragged in through here.
Through here.
It's funneled down through.
Funneled through. It increases the speed until the speed level you want.
Right.
And then it goes through the model. We measure the force, which is connected to a data acquisitioning system, and it's live connected to the screen. And then through the fan that we have here, it's taking the air out. And that's
I have a feeling it's going to get noisy here.
Oh, yes.
Yeah, let's see how this goes. So you're going to turn the air on now?
Yes, I'm going to turn it up. It's switched on, and I'm just slowly increasing the speed, so you can see it becomes noisier and noisier at higher speeds. And Yep.
And I think you might still be able to hear me on my mic, but it's getting quite noisy here. It's being dragged through here, and it's coming out here. Okay, you can stop.
Yeah.
So we set different speeds, and therefore we can kind of predict. Now, I'm interested in, what might be perceived as maybe a trial and error approach. You try one design, you see how it works, and you try something else.
Not really. No, it's not like that. It's not trying different designs to see what it happens.
Yeah.
No, it's actually thought through.
Yeah.
Designs that we go through, because design is a cycle.
Yeah.
So you come up with your design first. You do the tests, and you see, because sometimes it may not actually perform as you were thinking.
Sure.
So you go through an iterative process, not trial and error.
So you're bringing in now what you've learned in lectures, all the fundamental theory.
Exactly. You bring them in, you test them, and see if it actually works around
how you predicted.
Exactly. This is the ballpark and what you wanted to know. Then you get a feedback from that test or results that you have. You do the analysis, and you may want to iterate it back into the design.
Continued improvement.
To improve it. And then once it's done, then you can actually go with the bit larger scale.
So I'm getting a bit distracted by what's behind you there. Is this large scale? Give me a show.
This one is actually full scale. It's in the wind tunnels. So wind tunnels are coming in different sizes. This one that we have is an educational small test section, but there are wind tunnels that they're really full scale. And not only can you measure the forces, you can actually do some flow visualization, and you can get more insight into actually the flow around the objects. In this case, it's going to be a Formula car.
And then feed that back into your...
And then you can feed that back, because then before you go on the field to test it on the track, you can actually test it.
So one final question for you. How do students engage here? These labs are fully open, right?
These labs are fully open. They are part of the curriculum.
Yeah.
If they are actually part of the education, they come and use it for the courses, assessments, but it's more than that. We do have a lot of extracurriculum work. You just mentioned about the Formula essay as an example. We do have a very active student chapter. It's an
Institute of Mechanical Engineers.
So students are very much active in that, and they are voluntary and sort of extracurriculum are working on different projects. I'm sure when you show people the maker space, you can see they come up with an idea, they quickly make a 3D printing, they bring it, get tested, and also we have other packages, like the
it's a bit of a playground for engineers.
Yes, exactly.
Awesome. Thank you very much. No problem. We'll see you later when we're
I'll see you later.
Okay, good. Okay, so we're going to come through here. We've dealt a little bit with fluid mechanics, with mechanical engineering. I think we're going to now go into chemistry and chemical engineering. In fact, there's a good question, Fahid.
Hi.
Quick question for you. Somebody might be interested in chemistry, and maybe they want to know, well, what's right for them? Do a degree in chemistry or chemical engineering? Some people might not know there's a difference. What would you say the difference is?
Yeah, chemistry is a branch of science, as we know, and dealing with the substances, materials, atoms, molecules, interactions between them.
That's all chemistry?
All chemistry.
Right.
And chemical engineering is a kind of branch of engineering.
Yep.
We care about product and how we can optimize the production of the products coming from how we just produce products from the raw material.
From a raw material to the product.
To the product,
right.
yeah.
And what kind of processes then are, just types of processes that you might, when you take a raw material, what kind of processes are you talking about to getting to a full product?
There are different types of processes. We just care about the reactions.
Sure.
That dealing with reactors, because all the reactions happening inside the vessel, which is reactors. And other properties that we care through the process would be temperature, pressure. We try to control those properties. pH.
So the kind of how acidic it is, or
yes, if it's high, it's
react a different way.
If it's low, it's acidic. And we try to optimize this process.
So separation process, mixing
mixing, all those. And also we have biological processes, which is a part of the chemical.
And for me, when I think of the difference between chemistry and chemical engineering, I also think of scale. So chemistry might happen in trying to understand what's happening on
micro scale, if you're talking about that a little bit. But if you scale up the process in chemical engineering, you're talking about the large size of the
because if you're making, I don't know, products that are like, I don't know, chocolate, or if you're making ice cream, these things happen, or if you're making petrochemicals, these
anything
things
you're
don't
talking
happen.
about like products is chemical engineering, like plastics, oils, any products that you name it, cosmetic products.
Right, absolutely. Fragrances.
Lotions and so on. They're all chemical engineering involved.
Awesome. So I think there's a couple of examples you're able to show us.
Yeah, I want to just walk you through one of my colleagues.
Let's go. So I'll introduce you to Dr. Rebecca Lim, who is an assistant professor in chemical engineering in Heriot-Watt, Dubai. And I think you're going to take us through briefly how we make soap and what the role chemical engineers have in making soap.
Yes, so basically this activity normally I wanted to demo to the students that how a chemical reaction actually happens.
Okay.
So what I have prepared here is two different types of reactants. So this is a base solution, and this is going to be it's a type of oil.
So when you say a base solution, you mean as opposed to an acid?
So it's the opposite of acid. So
right.
Base solution here is typically we use we call it caustic soda.
Caustic soda, right?
Yeah.
Okay.
So it's a little bit of like bitter taste.
Oh, okay.
Yeah.
Right. And over here is just a typical like olive oil.
Yes. Yeah. So I'm having this olive oil mixed with a little bit of coconut oil.
Coconut oil. Okay.
Yeah.
Very good.
Yeah. You can use any oil or even like animal fat. That is also possible. So as long as the fat, you have the fatty acids.
Okay.
And then you mix with this base solution. The chemical reaction here happening is that when these two are mixed with a certain degree, and hence we normally place on this machine so that once it's actually happening the reaction, there will be chemical bondings between these two molecules.
Okay.
And up to a certain point, that it will actually start to form a little bit of like viscous liquid.
Oh, a viscous liquid, right?
Yes.
And then eventually what looks like a solid.
Because it's a reaction, so hence once you pour it in, and you probably need to let it for like a day or two.
Okay.
So to make sure that the reaction is completed.
Right.
So hence it's going to be quite safe for us to actually remove it, and then hence you can have a solid soap.
Excellent. So can we have a bit of a demo?
Yeah, sure. So first of all, I will just place this, and I'm going to put this in to make sure that the stirring is able to take place.
So that's a little magnetic stirrer that you've just put in there?
Yes, yep. So if you notice that, if just to show, this is how the mixing takes place.
Awesome.
Of course, the degree of mixing actually determines how fast the reaction can take place.
Okay, so you're trying to intensify this process by putting in a little magnetic stirrer there, and that's going to help these two mix, okay?
Else, if you're going to use just like your spatula to mix it by hand, it takes like hours.
It takes a long time, okay, fair enough,
And then hence you slowly put it in. And you will notice that the color starts to really change.
Straight away, yeah. And you're just speeding it up there a bit?
Yep.
So how long is this going to take?
Typically around 15 minutes, I would say.
Okay, so we're not going to wait 15 minutes if you don't mind. But then I see here you also have some things you can add in, these different colors.
Yeah, so if you like some a little bit more colorful, quite cheerful type of colorings, you can actually make some colorants into it, as well as some nice scents.
Some scents. What are you using there? Lavender, is there? Peppermint?
No, rosemary and peppermint. Yep. I have actually prepared some soap for you.
Let's take it out.
Yep. If you wanted to just try it out.
Well, I'm probably thinking today it's probably a good idea. This is something that we've prepared already.
Yep.
Our students have prepared, and given how important it is at the moment to wash our hands. And we were talking earlier a little bit as well about the sustainability issues that engineers. What would you think the role is of an engineer in sustainability?
Now, I would say that first of all, that for us as a process engineer, we are always concerned in terms of the entire process to transform the raw material into a useful product. We need to convert it into a effective manner, as well as sustainable in a way that we wanted to conserve the material loss, the energy, as well as the water itself.
So reducing or eliminating waste in every step that you go through.
Yep. Waste, material as well as energy.
Excellent. Very good. Thank you so much, Rebecca. That was really good. Thank you. Okay, so we'll continue our walkthrough now of engineering. I think we'll go to another process, and this one might surprise you, but it's coffee. We're going to make some coffee here. And Nazir here, also an assistant professor in chemical engineering, is going to talk us through that coffee is more of an engineer's product as opposed to an art. So step me through that. Maybe you could point to the chart behind.
Yeah, because chemical engineers, we are mainly working with the processes. So the process is to design a way or a process to convert raw material, and through each step we are actually adding value. So, so for example, if you are looking at green beans here.
So that's your raw material.
Your raw material. As green beans, they don't have too much value.
No.
Now, if we do some roasting and grinding, then we can produce coffee. And if you think about it, Coffee mainly is water.
Yes.
So very cheap raw material.
Yes.
Then you are producing large amount of final product that everybody wants to buy it. So that's what's happened.
Okay, so if I just summarize that a bit there, you have your raw material. You must engineer the processes. You know, what are you actually doing in roasting? What are you doing in grinding? Because essentially you want to extract these molecules that stimulate different parts of the tongue, which means it tastes differently, right?
Yeah, because mainly coffee is like we are talking about caffeine and with other materials that will stimulate the taste.
Okay.
So, and people, of course, they will differ about the taste of their coffee, how they would like it.
I know roasting to change the color, but what's actually happening as you go from this green to this roasted?
Yeah, the green actually, first thing we need to break the skin.
Okay.
So we are able to extract the flavor of it. And then, depending on the time of roasting, as can be seen here, we can go from green to very dark. And each roasting time or each type of roasting will give me a different taste.
Okay, but what's actually happening there? We're breaking, we're reducing the mass, you're extracting.
First of all, we're breaking the skin, so you will see that some of the like ash or shell will come at the end. Also, more roasting, we are releasing more volatile components, so we are concentrating the flavor.
Okay.
Yes. So, for example, if it's very light, it will taste more like, how to say it, it's more flavorish and as not coffee, as green beans. But as you are making it darker and darker, actually we are increasing the flavor.
Okay, and if you then were to, here I think we have...
but before that I can just show you, here is this roaster which we can control the time, and very simply we will start.
So that's you roasting it?
Yeah, well, I'm adding heat.
Adding heat, okay.
Heat,
which is energy, right?
Yeah, which is energy, so it will start breaking the skin and start removing some of my volatile components.
So we go from the roast then to the
grinding.
The grind over here.
Right. So you just have some your coffee beans here, and there is a scale which can go from coarse, grinding,
like a French press?
French press, to very fine, which is Turkish.
Right.
So if we can just and then I just go, and now this is my ground coffee.
Okay, so but instead of just following a recipe, you're deciding these things, and eventually this is somehow setting you up to be able to extract the molecules you want?
Yes.
Okay.
The idea is optimizing. So for each type of roasting, I can do multi-grinding types, and then based on this grind, I can go and do brewing. So brewing, I need water, of course, and then here I can add, for example, my coffee beans. Right, then very simply I will start brewing. So the hot water will go through my ground coffee and start extracting the flavor.
So how is it then that you say, so measure the difference? Do you just taste it, or are there...
No. First of all is the ratio. Now, for example, here I have 3 cups of water with that amount of coffee. Now, if I reduce the amount of water, I will increase the flavor. But how can I tell the flavor? There are different ways to test it. The easiest way is actually by taste. So sample. Or if you want to be more scientific, we can measure the acidity, which is the pH of your solution.
Excellent. And then you'd feed that back and you would say, well, what would I do different next time? Would I look at a finer grind, or would I roast for longer, and things like that, so that you can essentially extract exactly the molecule that you want to make. Because I think you were telling me earlier that you could make coffee quite sweet.
Yes. The idea is, if I was able to optimize my roasting, my grinding and brewing, which is water to ground coffee ratio, I will be able at the end to produce a perfect cup of coffee which is sweet without adding sugar.
I like that. All right. Thank you very much, Nasser. That was very good. Okay, now we're going to head outside And we're going to take a look a little bit more, maybe on the sustainability agenda, on the renewable energy engineering that we do. So we're about to head out onto the solar test site. I'm going to make sure my mic is definitely plugged in for this. It is. And we're going to go on the solar test site and look at the facilities that we have and the research that we do that are developing new technologies for energy engineering. So here on the solar test site of Heriot-Watt University, and we're going to talk a little bit about the technology that we have here and what our role is as a university. So, as we see some installations down here, these are bifacial solar panels, and these bifacial solar panels have an active layer on the top but also underneath. And what they're doing is they're grabbing a little bit more energy from the reflected solar from the ground on the bottom layer. Just under here. Now, these are largely untested and they're not characterized. And what's really important for renewable energy is that because it's capital intensive, you have to put a lot of money into the original installation. You kind of want to know how much energy you're going to get out of that over its lifetime, maybe 25 or 30 years. So the work that we're doing here is very important to characterizing and predicting as accurately as possible what that yield will be, how much energy you get over its lifetime. And that then gives confidence to people to maybe invest in these. And that's what's so important, to the integration of new renewables and sustainability aspects into the future. So we'll come downstairs now again. But just to say, this is a facility that gives students, whether they're at undergraduate level in our mechanical and energy engineering degree program, or at postgraduate level where we do an MSc in energy and an MSc in renewable energy engineering, it gives them that potential to have hands-on experience, to be working with the latest technologies. To the makerspace I think we have next. The technology is only part of the solution. It is making that technology affordable, giving it a good business case, and making it even desirable and an attractive product. Things like that go on in our makerspace. So let's take a look at some of the manufacturing processes that we have to play with here. So from the more traditional manufacturing, these are called CNC, or computer numerically controlled devices. This here is a lathe where we could cut out, and this one here is a milling machine. So you can see up here what the design was. I think this is just for fun. And you can see what this mill, which essentially is a drill that can move sideways as well as up and down, this is what it's been able to manufacture without any human intervention. We design it, we put everything in, and then we press go, and it goes. And of course, rapid manufacture is very important to everything that we do, and we're probably becoming more and more familiar with things like rapid prototyping. And here's an example of that, and it probably ties in with what we were talking about earlier. What we have here is the nose cone. You might be able to see that there, is the nose cone of one of our Formula student cars, or one of the prototypes that we would put into the wind tunnel. I think it is up here as well. So that's this section here. And like Mehdi was discussing earlier, depending on how you design that section, you will either get more or less drag, more or less downforce. Downforce gives you grip in these cases, and that's so important to making sure that you can translate the energy that's coming from the engine into translation, making it move down the track. So we can take a quick look at the nose cone that is now being printed here. It's called rapid prototyping, but it will take a couple of hours to develop a very high resolution, very smooth finish nose cone on this car. So when a student has an idea and they want to test that idea, they would design it. They'd relatively quickly get it printed on a machine like this, and then into the wind tunnel, and later you'll see that the final product would get tested on a track. We'll take a look at that later. So I'm going to move over here to some of the other manufacturing processes that we have and introduce you to Mus. Hi, Mus. So I see here you're busy designing the Heriot-Watt logo.
Etching them, yeah.
Tell me what's going on.
So I'm actually etching the Heriot-Watt logo on a case which I'll fabricate later for an enclosure. So it started from ABS plastic. I'm sorry.
This is just an
acrylic plastic sheet. So it just starts like as it is.
Okay.
And we can play. It's basically a really thin laser focused on to the material, so we can either etch them or cut them through the material. We can also use different types of materials like wood, paper, fabric.
Okay. So you would put something like this, something plain like this, into this laser cutter. You focus a beam on it and you translate that beam across it. And depending
in this case, we are using CO2 laser. There are different lasers, but we are producing the CO2 laser and really focusing them with the lens onto the material.
And then what does that do? So when it's very strong, it cuts through
it? Cut through the material.
And when it's less strong, it
etches. So it won't. So yeah, this Heriot-Watt logo, the font is actually etched. So you can see the material is intact still.
Okay.
But we can see the font.
Great. So you've cut this out along this side with a high power laser.
Exactly. And lower speed. So lower speed and high power actually cuts through the material. Higher speed and lower power etched through the material.
Etches. So you were able to then etch the kind of Heriot-Watt logo onto the back here, as you've drawn here. Can we see it?
Sure.
So that moving over and back is the high power laser. And are we all finished?
Yeah, we are done with that. So that's the logo being etched. We need a post processing of cleaning them and removing the dust and everything.
Okay, awesome, great. Well,
and once we are done with that, we can actually use a tool like acrylic bender. So let's say I want to make a case out of this. I can take this and heat them up across the template where I want to bend it.
So this was originally a flat plate as well?
Exactly.
And then
flat plate just as
you designed it and you cut it out to shape, and then you bent it?
Bent it, using the acrylic bender.
So if I was to bend that now, it'd probably crack?
No.
But
we need to heat them up, which this one does. So we actually heat them, the line across we will want to bend them.
Okay.
And then
because
after a couple of minutes it becomes soft, so we can actually use this process.
So at high temperature it becomes soft, you bend it into shape, it cools down and it holds its shape.
And it retains its shape.
So you can really quickly in a space like this come in with an idea.
That's the idea, whole idea behind here. Yeah.
Right, and then go out with a product.
Exactly. So prototyping.
Excellent. Probably won't go through everything, but we have things like vacuum forming over here. It's everything from sticker printing. I think there's a form carver over there, and there's a lot of programmable electronics. And we're going to come over to Suri now. Hey Suri. So Suri is an assistant professor in electrical engineering, electrical and electronic engineering. And you're going to take us through who I know to be Marty the robot. So can you introduce us to Marty and tell us what he does?
Yeah, actually artificial intelligence and machine learning, these are the emerging fields which requires a very strong foundation in engineering.
Yes.
So they should have knowledge of software and as well as hardware. Students should have the knowledge of both software and hardware. So it requires a lot of engineering skills.
Okay.
So say for example, these days any robot if you take, so the robot operating system interface can be run by Raspberry Pi. This is the Raspberry Pi.
So this is a piece of programmable electronics?
Yeah, it makes the robot a very strong onboard computing system.
Okay, so it's the brain of
which
Marty.
makes intelligent. Which makes it intelligent. So it can do a lot of tasks.
So you can program Marty, then you can give him some instruction?
Yes. So we can use, for example, Scratch, or we can write the program using Python or JavaScript. And we can interface with this. Like for example, this is a proximity sensor.
Okay, so well, take me back one step there, because you say you can give him instructions. What kind of instructions can you give it?
We can write the programs.
And what like to move forward?
Yeah. So say for example, here I will execute one command now. You can see the Marty there.
Okay, so you're getting Marty to switch his eyes.
Yes. So just to kick the ball or whatever you want to do, he will do it.
Yeah. Twitching his eyes. Oh.
Yes.
Nice. Well,
yes.
So basically, you've given him a few instructions there.
Very small command. So
to turn a motor or something, or to
it has servo motors. These are the servo motors.
Okay.
So it has 9 servo motors.
Okay.
Basically, the controller will control the servo motors. It will send the PWM signals. So that's why they should have the knowledge of both hardware and software. It is not enough if they know only the software side. So they should know. That's where the engineering lies.
So tell me about the kind of the feedback, and how do you make somebody like Marty intelligent? What's artificial intelligence about somebody like Marty?
Yeah. See, this This Raspberry Pi, which is a very strong onboard computer,
Sure.
so we can link with this.
Yes.
So robot operating system interface can be run by this Raspberry Pi, and we can connect the sensors. For example, here, you see, I have connected a bump switch.
Okay.
It is a sensor,
So-
and when it comes to the edge, he will not fall.
Oh, so when it gets to the edge, Marty knows where he is.
Yeah, where he
Because-
is. Yeah,
And
and
so he's aware of his environment.
Yes,
And then
exactly.
he can make a decision accordingly.
Yes,
So when I get to the edge of the table,
yes,
don't step up.
yes.
Okay.
And you can write a command to go, tell him to go back or turn left or turn right, whatever you want.
And if you integrate memory into
Yes.
Marty, then he would know not to go there again.
Yes, exactly. See here, I have connected a proximity sensor.
Proximity means that-
Proximity sensor. Any obstacle, if it comes, so he understands that there is an obstacle, and we can tell him to turn and take another path.
Exactly, right. So again, being aware of your surroundings, making decisions according to your surroundings.
Exactly.
That's the kind of intelligence that engineers now.
That is what computer vision and machine learning is.
Excellent.
So computer vision, we can have obstacle tracking.
Yeah.
You can insert a camera, and it can track the obstacles.
Also, it can even recognize
Yes,
obstacles.
yes. So obstacle tracking or motion estimation.
Excellent.
So many things we can do with.
Thank you very much,
Yeah,
Siri.
thank
That
you.
was really
Thank
good.
you so much.
Sento. Sento, I think you're going to talk to us a little bit about the artificial intelligence side of things, and maybe some of the the cutting edge research that is happening in electrical
Actually, my
engineering.
current research is actually focused on the development of various algorithms
Yeah,
using AI technology,
AI
especially
technology.
in
Yeah.
swarm robotics.
Swarm. Okay. So tell me, what is Swarm? Swarm is based on ants, isn't it?
Swarm robot is actually a pool of robots or a team of robots which
Yeah.
can be working together
Yeah.
to do any challenging task.
In the same way that ants work together in a swarm.
Exactly.
Okay.
It can be like a ants or birds. They can working together to move to a particular place or something like that.
So this to me is a science kind of biomimicry, right? We're
Exactly.
learning from
With nature,
the
yeah.
natural world and we're
Exactly.
integrating into bio.
You are right, yeah.
Okay.
And then the algorithms can be used for any challenging task, as I said, which kind of a firefighting or
Right.
any kind of search and rescue operations we can use them. They can go in a kind of a place in a team,
Yeah.
search in different places to identify a person or any kind of objects they can find using the search and rescue algorithms.
Excellent.
So here
Right,
actually
you're
we are
gonna show us a
having
demo, yeah.
a demo of swarm robots using for obstacle avoidance. So here we can see that these are actually a prototype of swarm robots. They can move in a path and they are not actually hitting each other. They can avoid the obstacles and then they can work together. And if anything change a color, they can change automatically. They can communicate with each other, and then we can use it for some path planning. You can see here we are
So
created a
this is a maze.
It's a maze.
And
So
we have one robot there in
Yeah.
the. if you wanna start it.
one can train first, then it can communicate with other robots, and then they can.
So we have the robot starting here, and he's finding his way around.
It's finding a best optimal possible path to reach their destination.
Okay.
So it won't hit at any of the obstacles, and then you can move towards the path, and it can learn from the environment, and then it can move quickly to the destination.
And importantly, you were saying in terms of swarm, then it will communicate that new path
Exactly.
to all its friends.
Exactly. For example, Google's are using, Google Maps using the best available path.
Oh,
It's using AI technology.
It is because it essentially traffic.
Exactly.
It's able to monitor the traffic and then feed that back into yours and giving you the best
Using
path.
the best available path it can go.
So the research you're doing here has lots of impact, not just in the robot itself.
Not in the
but-
robot, it can many automation processes. As I already mentioned, AI is actually exciting technology now, mostly used for any automation process,
Awesome.
starting from domestic to industry, and then we are using for mostly robotics field.
Excellent.
And they can able to use the intellectual abilities
Yeah.
to solve any problems and finding ideas, and then they can working.
And just so I understand that this is PhD level research, so cutting edge PhD level, but it's also the facilities and the technology we have then also supports all the projects that we do from undergraduate.
Yeah, exactly. So currently, I'm guiding 3 or 4 undergraduate projects which
Right.
are using AI technology.
Yeah,
And then now the trend, the recent trend is mostly on AI technology, how we are using electronics with AI or robotics with AI,
Yeah.
how we can progress or we can move on with that trend.
Cool. Then I suppose just one word then on, we're bringing in a new program in robotics, autonomous and interactive system. This is more to do with artificial intelligence and the interface between the kind of mechanical, the electrical and the artificial, how it all comes together.
This is a composite courses. It has include robotics, electronics, mechanical, computer science and AI technology.
Awesome.
Everything are inbuilt with this course. So it could be one of the very most wanted course for the present generation.
And we saw Popeye inside there, so it's quite exciting to see all these new facilities coming together. Thank you so much, Michael, Suri. Thank you. We'll see you guys later. So we're coming to the end of our tour. We hope we're giving you a bit of an insight into what it might be like to be an engineer in general and what it might be like to study in Heriot-Watt University as an engineer with all the different programs that we offer. We're going to go down here and culminate what I hope is going to be a competition. So back to Mohammed, who we saw earlier, and Mehdi. Show us what we have here. We have two cars.
Well, yeah, we got the cars ready for competition. Just like any other car, you'll need engine or propulsion. And here we are using canister with a compressed gas in it. We are loading them in the car, and this will be like really jet-powered car now.
Okay, so we have the compressed gas in there. We're about to pierce that, and that's going to gush out the back.
Right. And then that also the measurement takes the reaction time, because always race is not only about the best car.
That's right.
You'll need a good driver in. So would you like to see some racing?
I certainly would. So we have the red car and the grey car. They're quite different designs, and I mean we've probably done some analysis on this and what we think is going to be best. How are these ones made?
These ones 3D printed.
This one's 3D printed. Both of them.
Similar to the one that you've seen.
Okay, because some of them are using a lathe or a milling machine to take away material, but these ones are 3D printed from the bottom up.
These are 3D printed.
Awesome, good. And we can see, I suppose, different nose cones. We were looking inside there about the 3D printing of different nose cones.
Yeah, that's what I meant with the different designs. They're totally different.
Yeah, so the different nose cones will give you different drag, but they'll also give you more downforce and lift force, so that you're going to get either more traction, which you might want in a Formula 1 race, or here you might want a bit of lift so that you don't have the same kind of friction involved. Okay, so we think we're ready to go again with these two? Okay. I'm ready when you guys are, so I'm going to press this button, and then race is on. I think with 5 red lights, when they all go out, then it's over to you.
Yeah.
So just once. Or one more time?
Yeah.
So, get set. 1, 2, 3, 4, 5. And when you're ready. Hopefully you've gotten some small insight into all the different potential streams and all the different challenges that engineers have to play. When things return to normal, we will absolutely invite you to come onto campus and to experience, to take part in some of these activities and to be an engineer for a day. But for now, if you do have any questions about anything you've seen today or anything that we haven't covered, please throw it in below there, write it in below the Facebook Live, and we'll try to get back to you with some answers. So thanks for joining me today, and hope to see you soon.